Hello and welcome to another session of Introduction to Astrophysical Fluids. Previously, we discussed about convective instability, Rayleigh-Bénard convection problem. We also discussed about Jeans instability. In this discussion, we will focus on the instabilities in the interface of two fluids. This type of instabilities have a very important role in astrophysics. Okay, as I will say during the explanation of different type of instabilities and the corresponding analytical treatment. So the question is that if two fluids are existing together having some common interface, then if some very small or weak perturbation is made to that interface, how do the two fluid, now this is a system of two fluids, how do the two fluids respond to that perturbation? Okay, depending on their initial configuration, depending on their various kinetic and dynamic properties, and also depending on the nature of the perturbation, of course we can understand that there can be the possibility of some linear modes, linear wave mode, if the initial condition is stable. If not, then it will lead to some instability. Okay, this type of instability, sometimes it is called configurational instability or two fluid interface instability. Okay, so in astrophysical context, very frequently we come across regions where two different fluid layers they coexist. Okay, and that's why they define what we call a fluid interface, two fluid interface. Now, when the fluid coming out of a star or a stellar body, for example, as a stellar wind or due to the mass accretion, okay, during the mass accretion from a less dense star to a compact star, for example, then that fluid is in contact for a certain time interval, that fluid is in contact with the interstellar medium, right? And that makes actually another possibility of a fluid interface, two fluid interface. Similarly, another instance of astrophysical two fluid interface is that if, let's say, due to some explosion, now we know due to our previous discussion of supernovae that supernova explosion is one of the very one of the most important explosions in the framework of astrophysics. So due to that explosion, some fluids that always come out, okay, from that astrophysical objects, for example supernova, and when it comes out suddenly, then it makes also an interface with the ambient fluid, and now you know that actually it makes a shock or discontinuous type of thing most frequently. But if, let's say, that the system, if the explosion is if the explosion is in a such a phase that the shock is not yet formed, okay, and then actually you can still talk about an interface of the blast wave or the explosion wave fluid to the ambient fluid. Okay, and that is also true for galaxies. That means if some fluid is pitted from some galaxy due to some instability or some explosion, okay, some mass eruption takes place, then this this fluid will also make some interface with the intergalactic medium. Okay, now fluid of different densities can coexist at different layers of a star as well. So till now we were discussing the story of some fluid which are coming out of the star or some galaxy. Now even inside a fluid, in its different layers, you can actually see that fluids of various densities can coexist, and that defines another type of two fluid interface, okay, inside a star. And one very easy and prominent example is the sun, okay. Now in this discussion we will study mainly the effect of perturbation at those interfaces. Of course, you can understand that analytically handling all these issues, that the fluid's energy, the discontinuity, the compressibility, the effect of viscosity, the effect of rotation, okay, which is basically which creates the reality, is not possible in the scope of this course, okay. And this is actually the subject of active research. For this course, we will do something very simple and analytically very primary. However, the basic methodology will remain the same even if you try to sophisticate your treatment. Okay. Now, let us first consider, let us consider the interface of two fluids which are already incompressible and ideal. So if now, for example, we are talking about the two fluid interface and the corresponding instabilities, for example, for a highly compressible intergalactic intergalactic medium and some galactic fluid, then this is not a quite correct analysis which we will do here. But once again, that is just for the analytical, as a first step in analytical approach. You can start with taking very simple examples: incompressible fluid and ideal fluid. Now just remember the momentum evolution and the vorticity evolution equation for this type of fluids which are in gravity field. Okay, that is very important. Here we are considering that the fluid is in a body force field, which is the gravity. Okay. Then what happens? The two equations will be given by del V del T minus V cross omega, okay, is equal to minus gradient of P by rho plus V square by 2 minus gradient of phi g. So phi g is nothing but the gravitational potential. So minus gradient of phi g is nothing but small g, if you remember. Now rho is a constant because this fluid is incompressible, so it can actually come inside the gradient. Okay, V dot nabla V is now written in form of minus gradient of V square by 2, plus gradient of V square by 2 minus V cross omega, okay, where V cross omega is nothing but the minus of the Lamb vector, okay. Again, if you take the curl of this equation, you know that these two terms will go away and you will finally have del omega del T is equal to curl of V cross omega, right? Ideal fluid and incompressible fluid. No viscosity is there. Now, for simplicity, we know that, okay, now we know that as a property of such fluid, that if you start with zero vorticity, then, for example, at T is equal to 0, your vorticity is 0, then del omega del T will be 0 and your vorticity will always remain 0. So, we also assume for the simplicity and analysis that in our case, the initial vorticity is 0. And that is actually a bit very much simplistic with respect to the realistic cases. For the realistic cases, the initial, the fluids interfaces always have some vorticity in general, okay? And the system is very complex in general. Our system is very simple. And for this case, what happens that our fluid velocity is not only incompressible, that means divergence-less, but it will now have a zero curl as well. So this velocity field is divergence-less and curl-less. So V can be written as a gradient of a scalar velocity potential. Okay, that's exactly what is written over here. So V is equal to minus gradient of phi. So finally we get from 1 that minus of gradient del phi del t, so gradient and del phi del t they commute, plus gradient of v square by 2 is equal to minus gradient of p by rho minus gradient of phi g. Okay, because now our omega is 0 and we can write every v as this. So finally our equation can be written in terms of phi. Okay, although v square I am not changing here, just I keep it here. So finally you can write this thing that if you see again the gradient of del phi, the gradient of minus del phi del t plus v square by 2 plus p by rho plus phi g will be equal to 0. So the whole thing under the gradient will be a function of time only, because its gradient is 0. And that's exactly what I have written over here. Minus del phi del t plus v square by 2 plus p by rho plus phi g is equal to f of t. Now, note that this looks like Bernoulli's theorem, but for Bernoulli's theorem we use a steady flow in general, but this is a generalized version of Bernoulli's theorem which is true for non-steady flow as well. And here we don't need to make it true along the streamlines. This is true at any point, because now the omega is 0 identically. So you don't have to really take the dot products with the dl along the streamline, so that finally you can make the whole thing 0. If you remember the trick of Bernoulli equation, if you cannot, please have a look again. Here equation 4 is valid at all points of the flow field, whether we are tracing out a streamline or not. Okay, so the above relation is also valid for each fluid on the interface of the two fluids. Okay, and that's very important, and this one we will use later. Now coming back to our initial question, that what happens if we create some disturbance in the two fluid interface. Okay, how would the system of two fluid respond? Now this is not only depending on one single fluid, but there are two fluids. So here I am just taking, for simplicity, a planar picture. So along the x direction you have the interface. Okay, and so this green line is the interface of the two fluid. So one fluid is above z is equal to 0, another fluid is below z is equal to 0, and the vertical upward direction is of course z, as I already said. Now when this is not perturbed, then this interface is like that, and at that point we can say that both the fluids are having constant densities because of incompressibility, rho prime and rho, and also have some non-zero uniform velocity along x direction. That's quite okay. Actually the fluid is flowing on xy plane. Okay, but y is just, along y there is no considerable change or variation, and that's why simply this does not create any considerable change in the whole treatment. So y dimension we just keep aside for the time being. Okay, so u is equal to u times x cap, and u prime is equal to u prime x cap, and these two are constant vectors. Okay, because their magnitude is constant, their directions are constants. Okay, so these two are constant vectors. Okay, and actually, yeah, as you can see that they will also satisfy the initial condition of a steady state. As I said at the very beginning of the discussion in some previous lectures, when I started discussing about the waves and instability in the fluid, I said that the initial condition with respect to which the system should be perturbed must be a steady condition, steady state. Okay, and sometimes it can be steady and static state. Here we are talking about steady and non-static, but moving with a uniform velocity. Okay, and that is also a steady state. Now this line along at z is equal to 0 defines the interface of the two fluids. Okay, and so I have already said that the fluid above is characterized by rho prime and u prime, that is the the primed coordinates quantities, and the fluid below, this is characterized by the unprimed quantities, that is rho and u. Okay, this is the initial state. Now we perturbed slightly, although this looks a bit big. Okay, this is actually just for simplicity, and this is this is for exaggeration, so that you can understand. Okay, this is perturbed. Otherwise, this perturbation is very, very small. Okay, sorry, yeah, this perturbation is very, very small. That means this amplitude is very, very small. Okay, so if this in the interface, the fluid at interface is perturbed a bit, so for example the fluid from here is plucked until to this point, and the fluid from this is plucked in this direction up to this point, then what happens? Would the perturbation grow in time, or the perturbation decay in time, or the perturbation oscillate in time? That's our question. So as I said that the configuration satisfies the initial steady state condition, so we are all set for analyzing the perturbation around it. So now we perturb the interface from its initial position z is equal to 0 to some curve which is given by z is equal to xi1 x and t. So this curve is only depending on x and t. So along x it can have different values, okay, according to the different values of x, and it can also have an explicit time dependence. Okay, that is also possible. That is that depends on the nature of perturbation. If I just perturb the system by some time depending time depending oscillating element, okay, then this system will even if for a x is constant, okay, even if x is constant, for example here just the perturbation is made by some machine which is periodically oscillating or changing, okay, the perturbation value will change actually explicitly with time irrespective of the x value. Okay, that type of dependence is also included here. Now we will check that whether this modulus of this perturbation increases or decays in time. Okay, now the velocity potential at any point in the fluid below, that means the fluid with unprimed quantities, is given by phi is equal to phi 0 plus phi 1. So phi 0 is the velocity potential at the initial steady state, phi 1 is the perturbed part of this velocity potential. And this phi 0 is nothing but minus ux, because at the initial position you only have gradient of phi 0 which is equal to u x cap, there will be a minus. So if you correctly integrate that, so here you will have only one component d phi 0 dx, and that will be simply equal to minus u. So if you integrate properly, you will see that this will give you minus ux, and this is the initial part, this is the perturbed part, so the total part should be written as this, as simple as that. Okay, now after perturbation the fluid remains incompressible. That is of course true, otherwise there will be a big problem in our assumption. Okay, and also irrotational. Then we can say that even so the total phi, okay, will also, so if you know that if for a system like the V is such that divergence of V is 0 and curl of V is 0, then of course V is equal to minus gradient of phi, and since divergence of this is 0, you can actually write this is 0, so the phi actually satisfies the Laplace equation. Okay, so this is true for the total one. The first one is the first one is also satisfying the Laplace equation because of this functional form. This is easy to verify. Okay, and then the second one must satisfy the Laplace's equation itself. Okay, So the perturbed part of the velocity potential also satisfies a Laplace's equation. Same type of argument can be done for the fluid above, and for that we have similarly phi prime is equal to minus u prime x plus phi 1 prime, and Laplacian phi 1 prime is also equal to 0. Exactly what we have for the unprimed fluid, but this is the fluid above the interface. Okay. Now clearly, now let us, so we have some elements of analysis. Now we have to check some we have to consider some physical aspects. Okay, so clearly the velocity perturbation is caused by the perturbation caused to the interface. Okay, of course the velocity perturbation of the fluid, the velocity perturbation very close to the interface occurs. That means the uniform velocity u is now getting to some u prime or some v, actually some v, not u prime, sorry, u prime has a different meaning here. Okay, so v, and the same thing, the velocity of the fluid below the interface has some let me just repeat the sentence. So the velocity of the fluid below the interface becomes from u to v, and for the fluid above the interface becomes u prime to v prime. Okay, and that is because that the perturbation has been caused to the interface. Okay, and so these two must be connected, and that is the key of the whole treatment. So now how to connect them? For that we have to think a bit physics of that. So when the two fluid interface is perturbed slightly, a fluid element of the lower fluid which is situated infinitesimally close to the interface is also plucked. What is the meaning of that? Just go to this image. So when this interface is now plucked to this position, actually what happens, due to plucking, some fluid element which is infinitesimally close to this interface, okay, and which was the part of this fluid, okay, actually comes to this fluid. And actually you can see the same happens for the fluid above. For this case, the fluid above, some part of the fluid above, actually some fluid elements would come into this part, right? Because you see that that is very easy, because now this is the new interface. So new interface simply says that this will be then the fluid above, and this will be then the fluid below. Okay, so the fluid below actually penetrates a bit in the previous region of the fluid above, and here the opposite thing is happening. Okay, I think this part is clear. Okay, so in terms of the velocity potential, the vertical velocity component is nothing but minus del phi 1 del z. So this is nothing but minus gradient of phi, and along the z direction this is nothing but del phi 1 del z, right? So that is the velocity component, okay, of that is the velocity component of the fluid in terms of its velocity potential in the vertical direction, and that should be exactly equal to the Lagrangian velocity of the fluid elements. So this is because the fluid configuration is perturbed, so that the Eulerian velocity potential field is perturbed, is displaced. Now this one is because along with the Eulerian field is perturbed, the fluid particle is displaced actually, right? That is the physical consequence, and with that fluid particle we can actually say that the Eulerian velocity field at some point at z is equal to 0, nearly at z is equal to 0, will exactly be equal to the, due to perturbation, just for the perturbation, nearly will be exactly equal to the Lagrangian velocity, okay, of a fluid particle situated at that point. So once again, so when the surface is displaced here, actually with this surface, the fluid particle which was situated here now comes here. Okay, so now this is infinitesimally distant. Okay, so you can actually think that the velocity, the velocity component will be exactly equal here and here. Okay, and that is nothing but del xi del t. I mean d xi dt, that is the Lagrangian velocity. Okay, so they only have one component, and that is the vertical component, because the fluid element is only moving in the vertical direction, because the perturbation is made along the z direction. Okay, and then these two must be equal, so this is nothing but d xi dt. So d xi dt has two parts, del xi 1 del, okay, d xi 1 actually, because we are talking about the perturbation, so it is not xi but xi 1, okay, because they are first order. Okay, so del xi 1 del t plus u times del xi 1 del x. Okay, so why only this component is there? Because you only have the x component. Okay, and this is true only for z is equal to 0 or in the neighborhood of the old interface. Okay, if this is true, the same thing we can also write for the fluid above. So at interface, it will also have this type of equality of the Eulerian field and the Eulerian velocity field, okay, and the Lagrangian velocity field of the corresponding fluid particle which was situated at that point. Okay. Now you have two equalities, A and B. Okay. So for the perturbation, we now have to guess some solution for this perturbed quantity xi1 and phi1 and phi1 prime. Okay. For xi1, this is quite easy, because we can see that this is just a perturbation. This perturbation can only be a function of x and t, and both in x and t we don't have any any source of disturbance or something. So this is plucked and then it is totally released. So we can simply assume a plane wave type of solution, because finally once again these equations where you can see the xi1, they are linear in nature. So once again we can assume that they can be thought to be composed of Fourier components, and we take any one Fourier component which looks like this. Okay, so xi1 is equal to a e to the power ikx minus omega t. Now from the structure of A and B, that is something we have to go a bit slower. For the structure of A and B, so this is the part A, okay, and this is the part for B. One can actually, okay, see that xi1, so just a minute, one can actually see that the solutions can permit separation of variables as in the form of some z which is a function of small z times a function chi which is a function of x and t. If in this form one can see that the solution can be permitted, okay, if both phi1 and xi1 have the same x and t dependence part. If not, you can actually try. So you start with, for example, for phi1 you start with some z1 chi1 xt, and for xi1 you start with some z2 chi2 xt, and you will see that when chi1 and chi2 they are exactly equal, then only you can treat the whole system to in terms of the separation of variables. Okay, and actually to be very honest, in the x and t directions there are no, the perturbation is made along the z direction. Okay, that is true. So in the x and t direction there is no very prominent difference between the structure of phi1 perturbation and xi1 perturbation, or even phi1 prime. So they can have same type of dependence. Okay, so that is true that there is no hard and fast rule or hard and fast reason for which we can have this dependence identical, just because this analytics part becomes simple and analytics part become amenable or suitable for separation of variable method. Okay, now finally once we can say that, then we can actually have for both phi phi 1, phi prime and xi 1, okay, for all these three, this x and t dependent part will be exactly equal. Okay, so they should, so then for phi 1 and phi 2 we can actually use some, let's say some wz, okay, times e to the power I kx minus omega t, this type of thing, right? So because this part would not change, okay, and same thing for phi 1 prime. Finally, don't forget that phi 1 has to satisfy also a Laplace's equation. So finally, to satisfy the Laplace's equation in xz plane, one should have this one. Del 2 phi 1 del x2 is equal to minus del 2 phi 1 del z2, because we are not taking into account the y direction variation. So this one. And if you see that del, if I mean, so the x dependence of phi 1 is of the type of oscillatory here, as we have already said. Okay, if that is oscillatory, then if that is exactly equal to some minus m some minus m square, okay, so this one, so where m square is some positive quantity, so that is the condition, so that phi 1 can have an oscillatory solution in a function of x. Then del 2 phi 1 del z2, del 2 phi 1 del z2 must be exactly equal to simply m square, and which gives you an exponential dependence, either growing or decaying, of phi 1 with respect to z. Okay, and that's exactly exploited here to write this whole expression. So phi 1 can be written then is equal to c time e to the power minus I omega t plus I kx plus kz, and phi 1 prime can be written as another constant c prime e to the power minus I omega t plus I kx minus kz. Now we can easily understand why there is only kz and minus kz, but why there is plus and there is minus, that we cannot understand now. For understanding that, we have to realize that this type of perturbation, phi 1 and phi 1 prime, should vanish if we go really far away from the interface. That means when z's value, they are very, very large, then both phi 1 and phi 1 prime's z dependence should go away. And what is the solution for that? We just write in this way, so that for phi 1, this is the fluid below, so it deals with negative z values. So when z is very, very large, this term will go away, will be tending to 0. For phi 1 prime, it deals with z, positive values of z, so it has a minus sign, so when z is very large, so that z dependence will vanish. Okay, so that is the the justification. Then combining all our elements, finally the solution C and D can now be substituted in A and B equation. So this solution and this solution can now be substituted in these two equations, this one and this one. Okay, and if we do that properly, we can see that finally we have two algebraic equations like this: I times minus omega plus ku times A is equal to minus kc. Another one is I minus omega plus ku prime times A is equal to kc prime. Okay, so we have two algebraic equations, but how many unknown variables we have now? We have, non-variables, but how many unknowns we have? We have A, C and C prime. Okay, so we cannot eliminate A, C and C prime from these equations. Okay, that means we cannot solve this to get an equation or a relation between omega k and all the quantities of the problem, okay, which is known as the dispersion relation. So for having or obtaining the dispersion relation, we need another supplementary equation or relation. Okay, and that will be discussed in the next discussion. Okay, Thank you.